Welcome to qnawire.
Hi, so in this question we're asked to find the equilibrium pressure of H2 for the following reaction. We're going to have 2 moles of CH4 as a gas that is going to decompose into 3 moles of hydrogen as a gas plus C2H2 as a gas. And the information that is provided to us is the value for Kp, which is equal to 1 times 10 to the minus 8. So the first step in order to find these values is we're going to review how Kp looks in terms of the pressures of the components that we have here in our reaction. So Kp is going to be equal to the pressure of hydrogen to the cube times the pressure of C2H2 divided by the pressure of CH4 squared. We're told that the initial pressure that is going to be put into a reactor of methane is going to be 15 atmospheres of CH4 at a certain temperature. We know that the value for Kp is small, so we can consider that the decomposition of CH4 it is going to be minimal. That means that we're going to have very small quantities of H2 and C2H2 at equilibrium. That means the pressures are going to be much smaller than the 15 atmospheres that we're going to have. So, in order to solve this problem, we're going to proceed with a nice table. We're going to start with CH4 decomposes into H2, 3 equivalents, plus C2H2. Both of them are gases. So our ice table is going to look like, initially, I'm going to have an initial concentration, P naught, which is 15 atmospheres. We're going to have 0 of the products of the decomposition. The amount of change that we're going to have, sorry about here, I forgot it too, is going to be minus 2x because that is the amount that is going to decompose according to the stoichiometric coefficient. And over here, we're going to generate plus 3x and x. So at equilibrium, we're going to get P0 minus 2x, 3x, and x. So with these quantities, we can proceed and write down our value for Kp, which is going to be the pressure of hydrogen, which is 3x to the cube, times the pressure of C2H2, in this case, is equal to x, divided by the pressure of CH4 squared. So now what we're going to do is proceed with an approximation. Since we know that the value for Kp is very small, in this case is 1 times 10 to the minus 8, we are going to expect that x is going to be much smaller than P naught. So what we can do is approximate P naught minus 2x will be approximately equal to P naught. With this approximation that we're going to verify later with our result, what we're going to get is that Kp is equal to, doing the algebra over here with the coefficients, would be 27 times x to the fourth divided by P naught squared. From here, we can solve for x, and the value for x that we're going to find is equal to Kp times P naught squared divided by 27, and all of this to the 1/4. Replacing the values for Kp and P naught, we get that x is equal to 1 times 10 to the minus 8, P naught, which is 15 atmospheres. In this case, it's going to be squared. Here I'm not going to put down the units because we know that the result for x needs to be in atmospheres, divided by 27, and all of this to the 1/4. So the result that we're going to find here is equal to 0.017 atmospheres. Now we can proceed and look the equilibrium concentration of hydrogen, that is equal to 3x, the equilibrium concentration of C2H2, which is equal to x, and the equilibrium concentration of CH4. So for each of these cases, we can know the concentration since we have already solved for x. So the pressure of hydrogen at equilibrium is equal to 3 times x, which means equal to 0.051 atmospheres. Next up, we're going to have the pressure of C2H2 at equilibrium, which is equal to x, which in turn gets into 0.17 atmospheres. And finally, we're going to have the equilibrium pressure of methane that we have in our reactor, which is equal to P naught minus 2x, which gives us a value of 14.966 atmospheres. As you can see, the value for x that we have found is much smaller than 5% of the concentration that we have. That means that the approximation is going to be valid. Essentially, nothing is going to happen. And you can verify that the approximation worked because if you plug in these values into Kp, you're going to find that we recovered the 1 times 10 to the minus 8 that we found. So the equilibrium concentration for hydrogen, which is the one that is asked in this problem, is equal to 0.051 atmospheres. And if you need to round it up to one significant digit, you can write this as 5.1 times 10 to the minus 2 atmospheres. So that would be all. Thank you very much and have a good one.